Okay, where we left off in the last segment was units, units of measure. There are certain units of measure that we tend to use for small stuff like atoms and electrons because they're so much smaller than things that we usually deal with. And so we define the atomic mass unit, as I mentioned up above, as being the mass of one proton or the mass of one neutron. And that just makes things much easier to deal with on that kind of scale than trying to define the masses in more conventional units like grams or kilograms. I say approximately equal because protons and neutrons don't have exactly the same mass, but they're pretty close. So close enough for most purposes, we can say that they're the same as each other and the same as one atomic mass unit. If you want to know, really, actually here are the actual masses. For one proton is 1.0073 atomic mass units. A neutron is 1.0087, which is pretty close. And an electron is 0.00055 atomic mass units. So that's pretty small compared to the other two. You'll be able to look these numbers up if you need them. And an atomic mass unit in terms of more conventional units would be 1.66 times 10 to the minus 24 grams. And remember, a gram is about the mass of a standard size paper clip like that. That's about a gram, not including the dust bunny attached to it. And so think of 10 to the minus 24 part of that. That's an atomic mass unit. Or in terms of kilograms, because that's the official SI unit, that would be 1.66 times 10 to the minus 27 kilograms. Or in terms of pounds, a more familiar unit for most of us, 3.65 times 10 to the minus 27 pounds. So again, very, very small stuff we're dealing with here. And again, when we're calculating the masses of atoms, you only count protons and neutrons because the electrons are so small that it really wouldn't be worth the effort of adding them in. The charge on an electron is, again, negative 1.6 times 10 to the minus 19 coulombs. You don't have to know what a coulomb is just now, because we take that amount and we call it 1. And so the charge on an electron is minus 1, and the charge on a proton is plus that number. So that's plus 1. And a proton and a neutron, or a proton and an electron, exactly cancel each other out. The atomic number of an element, I've already mentioned, is the whole number in the periodic table. If you get a periodic table, and actually this is the periodic table that I'm going to give you on tests when we have them in class, and I will give you a copy of this before the first test, just so you'll know what information is on it and you can get familiar with it. This is very similar to the periodic table in our textbook, so you can look at that too, and it's pretty much the same either way. Anyway, in each square for each element, you'll notice the symbol for the element, like H for hydrogen, and you'll notice a whole number, and you'll notice a number with decimal spaces in it. The whole number is the atomic number. That is equivalent to, that is basically the definition of an element. If you have hydrogen, you have atomic number 1. If you have an element that's atomic number 1, you have hydrogen. If you have an element with 1 proton in the nucleus, that means it's atomic number 1, which means it's hydrogen. Okay, so and the atomic number is the number of protons in the nucleus. Each element has a unique atomic number, and that means each element has a unique number of protons in the nucleus. If you got 2 atoms and they've got the same number of protons in the nucleus, then they are the same element, no matter what else might be different. It is possible for atoms of the same element to have a different number of neutrons and a different number of electrons. But if they have the same number of protons, they're the same element. And on the other hand, if they have different numbers of electrons, or different numbers of protons, and therefore different atomic numbers, they are different elements, even if they have the same number of neutrons or electrons. And it is possible to find atoms of different elements that will have the same number of electrons or the same number of neutrons, but if they have different numbers of protons, they are different elements. If an atom is neutral, And actually, that's kind of redundant because by definition, an atom is electrically neutral, that is no overall electrical charge. Then that means that the number of electrons must be equal to the number of protons, and the number of protons is equal to the atomic number. So, and the symbol for the atomic number is Z. I forgot to mention that before. So for any normal atom, you can find the number of protons from the atomic number, and that also instantly gives you the number of electrons. There is also a mass number, and a mass number is actually the mass of a given isotope of an element. If you're dealing with a single atom of an element, then the mass number is just the number of protons plus the number of neutrons, since those are the heavy parts of the atom. And each of them has a mass that's close enough to one atomic mass unit. Okay. The mass number, it should be emphasized, is not the mass that's in the periodic table. We'll get to that a little bit later. That's slightly different. The mass number, or capital A as it's symbolized, only applies to one particular isotope of an element. Most elements have more than one isotope. And an isotope, again, is just atoms of the same element with different numbers of neutrons and therefore different masses. So if you've got an atom and you want to know the number of protons, that's just the atomic number. If you want to know the number of electrons, that's just the atomic number, also assuming there's no electrical charge overall on the atom. And the number of neutrons will be the mass number minus the atomic number, because the mass number is protons plus neutrons, and the atomic number is protons. So protons plus neutrons minus protons leaves neutrons. So that's how you can find those three things for any given particular atom or any particular isotope. When we're dealing with the element in general, or a large collection of atoms of the element, then we're normally dealing with more than one isotope. And we wouldn't use the mass number for one particular isotope. We would use the number from the periodic table, which is known as the atomic mass. And that is actually a weighted average of the masses of all of the different isotopes of an element. And that's why those numbers are not whole numbers. The mass number for an isotope is a whole number because it's just the protons and neutrons for that particular isotope. So that's a whole number. When you average all the different isotopes together and they're present in different amounts, and you average their masses together, you get numbers that have decimal spaces in them. So we'll get back to that in a moment. Ions. An ion is just an atom where the protons and neutrons are not equal to each other. So if the protons and neutrons are equal to each other, or sorry, protons, oh, wow, I really did that, didn't I? Protons and electrons, if the protons and electrons are equal to each other, then the atom has no charge overall. If the protons and electrons are not equal to each other, then the atom is actually called an ion, and it has an overall electrical charge. The charge on an ion can be given by the number of protons minus the number of electrons. And the charge will be due either to gain or loss of electrons from outside the nucleus by a neutral atom. And ions are always formed by gain or loss of electrons. The number of protons doesn't change because, well, for one thing, if it does change, you've got a different element, but also because the protons are hidden down there in the nucleus and they're really hard to get to and are really hard to add or remove. So it's always a change in the number of electrons that turns an atom into an ion or an ion into a different ion. So if the number of protons is greater than the number of electrons, you have a positive charge on the ion because you have more positive charges than negative ones. That's known as a cation. And for instance, the element sodium, if you look at sodium in the periodic table, it's atomic number 11. which means that it normally has 11 protons and 11 electrons. So they cancel each other out, so there's no charge overall. But sodium doesn't have a very firm grip on its electrons, and it often loses one of them, at which point it has 11 protons and 10 electrons. So it has one more positive charge than it has negative charges, which results in a +1 charge. And that is what we call the Na plus ion. If the charge is +1, you don't have to write the 1. You can just write plus. If it's +2 or +3 or something like that, then you'd have to write the number along with the plus sign. If the number of electrons is greater than the number of protons, then you have more negative charges than positive charges. You end up with a negative charge overall on the ion, and that's known as an anion. And for instance, chlorine. Chlorine has atomic number 17. So it normally has, oops, I got the wrong element there. There. Chlorine has atomic number 17. So it normally starts out with 17 protons and 17 electrons, which cancel each other out. So chlorine atoms have no overall electrical charge. But chlorine really, really wants more electrons. And so it often gains an electron from some other element. And it ends up with 17 protons and 18 electrons. So in other words, it has one excess negative charge, which lands chlorine with a makes chlorine atoms into an ion with a -1 charge, or the Cl- ion. And again, if the charge is -1, you don't have to write the 1, although you can if you want to. But if it's, say, -2 or -3, then you do have to write the number as well as the sign. Sorry. So if you take just number of protons minus number of electrons for chlorine, that would be 17 minus 18. 17 minus 18 is -1. So there you go. The symbols for the elements are the abbreviations that are used in the periodic table. Each element has its own unique abbreviation, and sometimes they've had to go to fairly extreme lengths to get an abbreviation for an element that is unique and not the same as some other element. The symbol will consist of 1 or 2 letters representing the name of the element, mostly in English or in foreign languages where the name is, compatible with the English name. Sometimes in another language. Latin would be the most common alternative to English, but there are some that are derived from Greek or German, or I think one might even be from Sanskrit. Anyway, for each symbol, you'll notice the first letter of the symbol is always capitalized. Doesn't matter if there's only 1 letter in it or 2, first letter capitalized. Second letter, if there is one, is not capitalized ever. So for instance, cobalt, which is a metal that's kind of similar to nickel, it's right next door to nickel, has the symbol capital C, lowercase o. That's an important distinction to make, because if you forget that that second letter is supposed to be lowercase, then you can end up with capital C, capital O, and that is actually the compound that consists of 1 atom of carbon and 1 atom of oxygen, and that's carbon monoxide, a deadly poison. So you don't want to confuse cobalt with carbon monoxide. They're pretty different, actually. The symbols, can represent 1 atom of an element, or they can represent the element collectively. So if you, it depends on the context, really. If you're writing it as part of a chemical reaction, then normally the symbol represents 1 atom of the element. But if you're using it like a label on a bottle, then it could represent the element in general. If I had, a reaction where I'm writing Na plus Cl equals NaCl, that would represent 1 atom of sodium, the Na would. But if I have a jar of sodium and I put Na on it, then obviously sodium just represents the identity of the stuff that's in the jar. So you could use the symbols either way, just like you can with the name. The table on page 82 has a list of common elements and their symbols. I'm not going to go over them. You don't need to memorize them, but it would be a good idea to become familiar with them so that you can recognize them more quickly. It'll save time, which could be a factor. Well, it can be a factor for anything, tests, homework or quizzes, but especially on a test, which is going to be given in the classroom. So we'll have limited time to do it. It would also be a good idea to, get familiar with the periodic table as much as you can. Again, you don't have to specifically memorize any of it. I'm not going to leave blanks and ask you to fill them in or anything, but it'll help you find elements more quickly if you know how it's organized and generally where things are. A good approach might be to take a copy of the periodic table and just post it on the wall over the desk where you usually do most of your work. And then you'll find that as you start daydreaming and staring into space, you'll be staring at the periodic table, and you can actually take in quite a bit of information that way. Okay, there are symbols for isotopes, which involve the symbols for the elements, but additional information too. Because an isotope is an atom of an element that has a particular specific mass, you want to include the mass of the isotope in the symbol if you're talking about only one particular isotope instead of all of the atoms of that element collectively. So the symbol of the isotope is just the symbol for the element accompanied by its mass number of the isotope. And it can also be accompanied by the atomic number, but that's kind of redundant because the atomic number defines the element just like the symbol does. If you have carbon, then you have an element with atomic number 6. If you have atomic number 6, then you have carbon. So including both the C and the 6 is kind of redundant. Gives you the same information twice. When I type these isotope symbols on a test, I tend to include only the mass number and not the atomic number because it is a real pain in the backside in Microsoft Word to get it to put a superscript and a subscript right over one another. It's not really worth the effort because, like I said, the atomic number is kind of redundant anyway. The number on top would be the mass number, and it's written as a superscript before the symbol of the element. And if you include the atomic number, that would be written as a subscript before the symbol of the element. The name of an isotope is usually given as the name of the element followed by the isotope mass or the mass number. Okay, so as an example, for the isotope carbon-12, the most common isotope of carbon, the symbol would be 12/6C. But I'm going to put the 6 in parentheses because that may or may not be there, and it's not really necessary. So this is an isotope of carbon that has a mass of 12 atomic mass units in each atom. And that means the total of protons and neutrons is 12 for that particular isotope. But there is also an isotope of carbon known as carbon-13. And the symbol for that would be 13/6C. But again, the 6 might be missing. So 13C would be the symbol. And that means that you've got a total of 13 protons and neutrons in an atom of this isotope for a total mass number of 13. And then also there's carbon-14. This is the isotope that's used for radioactive dating of archaeological objects. And the symbol for that would be 14/6C. But again, the 6 might not be there. And that means that this isotope has a total of 14 protons and neutrons. And so it has a mass number of 14. And as I've said, mentioned before, just to emphasize, most elements have more than one isotope. There are really only a very few elements that have only one isotope. And the abundances of some of those, or the identities and abundances of some of those isotopes are given in the table on pages 83 to 84 in the textbook. And you can look that over just to sort of see, oh yeah, there really are more than one isotope for most elements. The vast majority of elements that have more than one isotopes, in most cases, it takes the form of one isotope being overwhelmingly predominant and the other isotopes being present only in small amounts. But the smaller amount, the minor isotopes are usually present in large enough quantities that they can cause the average atomic mass, that is the atomic mass that appears in the periodic table, to be to require decimal spaces. It's not a whole number. Notice that these masses, the atomic masses given in the periodic table, those are not whole numbers. Okay, and there are only a couple of cases where they are whole numbers. Oxygen is a whole number by chance because that just happens to be how the isotopes average out. Fluorine is a whole number because fluorine is one of the few elements that really does have only one isotope. So it's a whole number because that's the mass number of the only isotope that exists. Again, you can find the protons, neutrons, and electrons for a given isotope by just using the equations that we used before. The number of protons would be the same as the atomic number, which might be included in the symbol for the isotope, or you might have to go to the periodic table to find it. Number of neutrons is just the mass number of the isotope minus the atomic number of the element, or A minus Z. And the number of electrons would be the same as the atomic number. Okay, so that would be Z, as long as it's a neutral atom and neutrally uncharged atom and not an ion. So for carbon-12, the number of protons would be 6 because it's atomic number 6, which you can, again, also get from the periodic table. The number of neutrons would be mass number minus atomic number, so that's 12 minus 6, or 6. And the number of electrons would be the same as the number of protons, which is 6 in this case. For carbon-13, the protons and electrons, again, are 6 because it's still carbon. But the number of neutrons will be 13 minus 6, or 7 in this case. For carbon-14, protons and electrons, again, are 6 because it's still carbon. And neutrons would be 14 minus 6, or 8. So you can see the mass goes up from carbon-12 to 13 to carbon-14 because the number of neutrons is going up for each one. Okay, so the atomic mass is the number in the periodic table, and it's the number with the decimal spaces in it in the periodic table. It's the weighted average of the masses of all of the isotopes of that element that exist. And specifically, it's weighted for the proportions or abundances of each isotope. So each isotope exists as a certain percentage of the overall element. So maybe in the case of carbon, 99% of all carbon atoms are carbon-12. But then about 1% are carbon-13, and a trace like 0.001% or 0.01% rather are carbon-14. So you have to take those masses and multiply them by the abundances and then add all that up. So this is a fancy mathematical way of writing what we're doing. For carbon, again, what you do is you take the mass of each isotope, multiply it by its abundance. Be careful though, abundances are usually given as percentages. When you use them mathematically, you have to convert to the decimal form of the abundance, which is just a percentage divided by 100. So carbon-12 has an abundance of 98.89%. That's 0.9889 as a decimal. So you take 12, and I stuck some extra decimal places in here because this is considered to be exactly 12. So I stuck those in so we could use more decimal spaces in our answer. 12.000 times 0.9889. That's 11.8668. And then you take the mass of carbon-13 times its abundance as a decimal. So it's 13 exactly times 0.011, which is 0.143. And then you take 14, which is the mass of carbon 14, times its abundance, which is 0.0001, and you get 0.0014, and you add all of those up, and you get 12.0112. And a lot of periodic tables will report the mass of carbon as 12.011. Ours cuts it down to 12.01. But anyway, that is how you get the number. Okay, and the number reflects the fact that a vast majority of it is carbon-12, but there's also some 13 and 14 in there, which raises the average number up a little bit from 12. Okay, the book, for some reason at this point, wants to get into a discussion of mass spectrometry. I think we can save that for graduate school if you want to pursue that kind of thing, or at least upper level chemistry. So we'll skip the mass spectrometry for right now and go on to the subject of chemical formulas, or formulae if you want to be use the proper Latin form. I see now that we're probably a little over time on the time for this segment of the video, so I'm going to stop it there and we'll pick up here when we come back with the third segment.